Well, good afternoon, everyone. Welcome to the Australian Institute of Physics Theoretical Physics Seminar Series for 2021. I'm David Tilbrook from the Department of Fundamental and Theoretical Physics at ANU, and I'm hosting this series of seminars on behalf of the Australian Institute of Physics Theoretical Physics Group. I would like to start by acknowledging the people of the Ngunnawal Nation, the traditional custodians of the lands upon which ANU is located here in Canberra. And of course, we also acknowledge the traditional custodians of lands around Australia. We like to pay our respects to their leaders, past, present, and emerging. I'd also like to acknowledge Murray Batchelor and the other members of the organising committee who have done so much good work to identify fascinating topics and well-qualified speakers to speak about those topics. As I mentioned above, this seminar series is being organised by the Theoretical Physics Group of the AIP. If you're interested in theoretical physics, I would encourage you to join that group. It's free, of course, if you are a member of the Australian Institute of Physics. And to do that, just log into the membership portal on the AIP website. You'll see the Theoretical Physics Group name under topical groups, and you can add yourself to that group there. Then you'll receive any advanced information about upcoming seminars and so forth. So far in this series of talks, we've had seminars on a range of topics, such as dark matter, particularly from a particle physics point of view, the Fermilab G-2 experiment and its possible consequences for the future of the standard model of particle physics, quantum stochastic resonance, and the most recent seminar was given by Professor Gerard Milburn from the University of Queensland, who spoke about the thermodynamics of clocks. It was a very interesting talk in which Gerard looked at some of the properties of clocks and the implications for our understanding of time, particularly from a physics point of view. All of these talks have been extremely good, and if you missed those or you would like to see them again, they're available to watch on the AIP YouTube channel. Today's speaker is Emeritus Professor Carl Bender from Washington University in St. Louis, Missouri. Professor Bender is the Konecker Distinguished Emeritus Professor of Physics at that institution. He's also a joint professor of physics at the University of Heidelberg and a visiting professor at Imperial College and King's College, London. As probably many of you would know, he has made countless contributions to theoretical and mathematical physics in areas as diverse as asymptotic analysis, differential equations, applications to theoretical physics of perturbative methods, and of course to the mathematical structure of quantum mechanics, just to name a few of many topics that he has made significant contributions to. But I think it's true to say that he's best known for his work on PT-symmetric versions of quantum theory, in which it is demonstrated that the Hamiltonian for quantum systems need not be restricted to self-adjoint operators to ensure the existence of real eigenvalues, provided that the Hamiltonian satisfies certain PT-symmetry properties, which I'm sure that Carl is going to talk about in just a few minutes. I think this is a particularly satisfying characteristic of this new approach because, as many of you would know, the requirements within standard quantum mechanics that operators corresponding to physical measurements be self-adjoint is really an axiom of quantum mechanics. It's hard to gain any additional physical intuition as to why quantum mechanics would have that structure other than we want real eigenvalues to predict the results of experiment. But with the requirement of PT-symmetry, this becomes more obvious. And the theory has far-reaching implications for quantum mechanics and quantum field theory and makes predictions which have subsequently been predicted by experiment. So to shed some light on this fascinating development, Professor Bender's topic today is on PT-symmetry. Over to you, please, Carl.
Thank you very much for the introduction. So I should just begin with some acknowledgements. I want to thank you for your invitation to speak to you. Although I usually begin a talk by saying it's nice to be here, but it isn't nice to be here. I wish I were there. I really wish I were speaking to you live, and I'm not happy sitting at my desk rather than standing in front of you at a blackboard. One of my friends said to me that they felt that a really good talk should have at least one very deep theorem and one really good joke. And you know you're giving a good talk if the audience can tell the difference. Given that I'm sitting over here, I don't know whether or not I'll be able to tell whether or not you know the difference, but I'm going to try. So here's the 30-second summary. As you know, energy in physics is crucial. It's the key thing. And when you measure it, you should get a real number. And in quantum mechanics, we assume, therefore, that H is Hermitian in order that its eigenvalues be real. But I'm going to argue that there's another less mathematical and more physical possibility, and that is that H is PT-symmetric. And when I say more physical, I mean hermiticity is a very funny requirement. It says that if you take the Hamiltonian and you take its transpose and then you take its complex conjugate, you get back the Hamiltonian. That's a very mathematical statement. It doesn't sound like it was written by a physicist, okay? But when you say PT-symmetry, you mean space-time symmetric, okay? And that's a very physical sounding condition. Okay, so as you know, Newton over here, I hope you can see my cursor. Newton discovered gravity, but also Einstein rediscovered it. He showed that time is actually money, okay? And you know that you're instructed to study the Lorenz group. What is the Lorenz group? Well, the homogeneous Lorenz group, which is probably the most fundamental group there is the set of all real 4x4 matrices that map the space-time point x, y, z, and t into x prime, y prime, z prime, t prime, okay? In such a way that this quantity, x squared plus y squared plus z squared minus t squared, is preserved. It's invariant under a Lorenz transformation, okay? That's the light cone condition, okay? And also, as you know, parity, which is space reflection, and time reversal, T, are elements of the homogeneous Lorenz group. And that's clear because under parity, you change the sign of x, y, and z, okay? But that doesn't change the quantity x squared plus y squared plus z squared minus t squared. And time reversal changes the sign of t. And the same is true, okay? So these P and T are very important physical operators because they are elements of the Lorenz group, okay? Now, the Lorenz group is pretty fancy, okay? It's a continuous group, contains an infinite number of elements, but it consists of 4 disconnected parts, okay? So these are all of the 4x4 matrices that are connected to the identity. This is a subgroup of the Lorenz group. It's called the proper orthochronous Lorenz group, okay? And this is a group. This is a subgroup of the full Lorenz group. But the elements of the Lorenz group also include these, and these, okay? So this is all of the elements of the proper orthochronous Lorenz group multiplied by T. And these are all those elements multiplied by P. And these are all those elements multiplied by PT, okay? So these are 4 disconnected parts. By the way, this by itself is not a group because it doesn't contain the identity. Same with this, okay? But now, what happens if we take all those matrices, those 4x4 matrices, and allow them to have complex entries, not just real entries, but complex entries? That's called the complex Lorenz group. And the complex Lorenz group consists of not 4, but 2 disconnected parts. So if you are working with the complex Lorenz group, there is a continuous path from all of these elements through the complex Lorenz group to all of these elements. Okay, and there is another continuous path from all of these elements to all of these elements. And this is very important because you use the complex Lorenz group to prove the famous CPT theorem. This is where the PT in the famous CPT theorem comes from. Okay, you have to do an analytic continuation from these elements to these elements. Okay, so you see that PT symmetry is intimately connected with complex variable theory in mathematics. Okay, now here's the point of the talk. Mathematicians find it enlightening to extend the real number system to the complex number system because it helps us to understand the real number system better. In this talk, what I'm going to do is to extend conventional real physics to complex physics. And if we do this, we can understand quantization better. I'm going to give you a whole new picture of quantization. We can understand the divergence of perturbation theory. We can generate new kinds of quantum theories called PT-symmetric quantum theories. We can tame instabilities and much, much more, but that will have to wait for some other talk, okay? So let me begin my talk with an outline. This talk is organized in 3 separate parts. Here they are. There's the beginning, the middle, and the end. Okay, I hope that takes care of it. Okay, so as you know, the conventional world is described by real numbers. Okay, for example, election results. Those are all real. There are no imaginary ballots, or except in the United States, perhaps. Or IQ test results, okay, or money, okay? We only use real numbers. In fact, here's an example of a real quantity of money, which you can find in Brazil, okay? But complex mathematics is very powerful, and it explains all sorts of new and interesting things about real mathematics. It explains the convergence of Taylor series. It determines the asymptotic behavior of real integrals. It enables us to sum divergent series. It explains real functions, such as the square root function, and much, much more. Just huge amounts of additional stuff, but I won't talk about it today. So what about Taylor series? So here's an example of a very nice simple function, 1 over 1 plus x to the 4. It looks like this, very smooth function. And you notice that if you expand this into a Taylor series, the radius of convergence of the Taylor series is 1. Okay? However, even though that's true, even though this is a perfectly smooth function for all x, for all real x, okay? So why is it that the radius of convergence is 1? And of course, you all know the answer. The answer is that you have to go to the complex plane. And I'm going to show you some examples. These are complex planes, okay? If I were visiting you in Australia, I would probably take this one. This is a really wonderful plane. It has only one minor defect, and that is that the passengers ride over here, but the toilets are over here. But other than that, it's wonderful. So it can be used to find the asymptotic expansion of various integrals. And here's a really wonderful example. This is a real integral. There's nothing complex about this integral. And you notice that it's integrated, we're integrating from -1 to 1. In the integrand is this Gaussian here. And there's a cosine of a cubic, okay? And this integral is a function of x. And we can ask, how does this integral behave as x goes to infinity? Now, you might think that for very large positive x, this Gaussian here ensures that the only contribution to this integral will come near t equals 0. Otherwise, this exponential is this is exponentially small. There won't be any contribution. And if you make an argument like that, you will get the wrong answer. It is not true, even though it looks like it's true. Okay. Now, in fact, the asymptotic behavior of the integral for large x is very simple. It's just this e to the minus 2x times the square root of pi over x. Okay. But in fact, without complex variables, if you can prove this with absolutely no reference to complex variable theory, you should probably publish that result, because it's a very difficult result to obtain using real variables alone. And that's because for large x, the contribution is not localized at t equals 0. Okay, so where is the contribution? Well, you have to use the method of steepest descents. You have to extend the path of integration into the complex plane, and you follow a really interesting path. You start out at -1, but instead of running along the real axis to +1, you go off to infinity in the complex plane along a steepest descent path, and then you come back up and pass through a saddle point at I, which is where all the contribution to the integral comes from when x is large and positive. And then you go off to infinity again, all along a steepest descent path. And then you come back up to infinity, back up to 1. Okay, so you have to deform that contour into this kind of mushroom-looking contour. Okay, and without doing complex variable theory, to get out the answer is extraordinarily difficult. Okay. What's another use of complex variable theory? Well, you can sum divergent series. Here are a bunch of divergent series. They all have finite sums, even though the series diverge. Okay. Now, the first two series are interesting because you can deduce their finite sums using real variable techniques only. But the second two really requires complex variable theory. Now, I'll show you the answer. These are the sums of these series, okay? But you need to use complex variable techniques to find these sums. And by the way, these are sums that appear in physics problems. This is not a mathematics talk. This is a physics talk, okay? And if you wish to calculate the Casimir force, for example, which you can measure in the laboratory, you need to do sums like this, which are modal sums, okay? And you need to actually sum this divergent series and get this finite result in order to verify your laboratory measurements. Okay, complex variables also helps us to understand real functions. So an example of such a function is the square root function. So what's peculiar about this function is that there are apparently two answers. You know, the square root of 9 is plus or minus 3. How do you explain this? How can a function have two possible answers? And the answer is that the square root function must be defined on a Riemann surface, which consists, in the case of the square root function, of two complex variable sheets, two complex planes cut and glued together. Okay, so the topology of this Riemann surface is like that of a Mobius strip. If you go around twice, you come back to the starting point. So for example, if you start on the lower sheet and you start going around the origin, you're now in the top sheet. And then as you continue going through the cut, you come back down to the original sheet. Okay, so you have to go around twice. Okay, and that means that I'm going around on the lower sheet to come back to where I started. Two pi rotations, okay, 720 degrees. I can give you an example of how two rotations brings you back to where you started. If you take a cup of water and you rotate it around, so I'm going to rotate it around in a clockwise fashion in my frame of reference here in St. Louis, okay? So I'm going to rotate it. I should move back so you can see it. Okay, I'm going to rotate it around, all the way around 360 degrees. and my arm is twisted. This hurts, okay? This is not the original configuration. So I continue going in this direction, another 360 degrees, and now we come back to where I started. Okay, a very simple example. So there are lots of things, of course, that come back to where you started when you rotate by 4 pi, not 2 pi. Things that remain the same would be, for example, a Mobius strip stake. Okay, or to be serious, an electron. If you rotate an electron by a full 360 degrees, it's not the same electron. It's a different physical configuration. But if you then rotate again by 360 degrees, you get back to the original configuration. Okay, now, so those are just a bunch of examples, but I'm trying to argue that complex variables is very important in mathematics, but it's also extremely important in modern physics. You know that the complex number I appears in modern physics. For example, in the Heisenberg algebra, if you multiply x times p and subtract p times x, you don't get 0, but you get something proportional to I. Okay, and I also appears over here in the Schrodinger equation. Don't look at this, just look at the Schrodinger equation. Okay, and by the way, Mr. Wigner told us that time reversal is very important. It corresponds to complex conjugation. That is, time reversal changes the sign of I. It replaces I by minus I. And you can see why this is true, because if you change the sign of I, that corresponds to changing the sign of t in the Schrodinger equation. Over here, if you change the sign of I, that corresponds to changing the sign of p. The particle is moving in the opposite direction under time reversal. And so this is consistent under, so you can see that the Heisenberg algebra is consistent with time reversal. And that's crucial in quantum mechanics. Okay, now in quantum mechanics, what do you learn? In an introductory course, you learn that a particle in a potential well has quantized energy levels. You also learn that going from one level to another is a discrete quantum leap, okay? But what's nice is that complex analysis provides a much, much deeper understanding of quantization, okay? So let me explain it to you in a very simple way. Imagine you have just a two-state system, okay, having energies A and B. This is the Hamiltonian for the system. These are two non-interacting components of the system with energy A and B, okay? Now, let's couple these two components of the system with a coupling constant G, okay? And now let's ask, what are the energy levels of this Hamiltonian? So you know how to find the eigenvalues of a 2x2 matrix. You take the determinant, okay? That gives you this secular equation. You solve it for E and you find the two energies, okay? And here they are, okay? And you notice that a square root has appeared. And you notice that there are square root singularities, as I told you, in the complex coupling constant plane. So not on the real axis, but in the complex coupling constant plane, there are singularities where the argument of the square root vanishes, and that happens at G equals plus or minus A minus B over 2 I, okay? So there are singularities, okay? And that's the branch point of the complex Riemann surface for that function. This is what the Riemann surface looks like. Here are the two singular points. There's a branch cut joining these singular points, okay? And of course, you can go around twice. This is a square root and you come back to where you started, okay? And now let me point out that on this complex G, complex coupling constant Riemann surface, the energy levels are not discrete. Look, they're continuous, okay? The energy levels E of G are continuous functions of G. they're not discrete, okay? So in what sense are the energies discrete? Well, there are two energy levels. For this particular value of G, you notice that there are two answers when you take the square root function. As a function of G, E is equal to either this value or that value, but you can go continuously from this value to this value very easily. You start, let's say, at the lower energy level, you go continuously on the Riemann surface, you go around and around, and now you're at this upper energy. So there's no jump, okay? You think that there's a jump if you only want to do real mathematics, but if you want to extend real mathematics into complex plane, there are no quantum leaps. Everything is nice and smooth. And what you see is that quantization is topological. Why are there two energy levels? It's because they correspond to the two discrete sheets in a Riemann surface, okay? And these square root singularities, in fact, explain lots of things. They explain the divergence of perturbation series, and in fact, complex variable techniques can be used to sum a divergent perturbation series, get a finite answer, okay? So if you'd like to generalize this to the real world, imagine a parking garage. He has trouble doing that in a physics talk, I suppose, but you don't. You can imagine a parking garage as a multi-sheeted Riemann surface, and you can go from any one energy level to any other energy level, and this is a generic result, okay? So why do we think that quantum mechanics has discrete energy levels? It's because we like to cut the parking garage right here. And if you cut the parking garage along the real axis, then indeed it looks like you have discrete energy levels. You can see them. But if you generalize to the complex plane, everything is nice and smooth, okay? So what is taught in conventional quantum theory courses is rather limited. Unlike what is taught in these courses, the energy levels smoothly deform into one another under analytic continuation. You can go from any one energy level to any other energy level by a smooth continuation on a Riemann surface, okay? Now, you may think this is just mathematics, but it isn't mathematics. This is physics. In fact, in this paper right here, this is a physical review letter back in 2012, they were able to take a physical problem which had discrete modes, which was a microwave cavity, a microwave billiard, and they were able to analytically continue from one mode to another mode by simply varying the parameters of the problem. And in fact, you can read these papers in Nature back in 2016. These are even more beautiful than this paper, because in these papers, they were actually able to do it in real time. That is, they just twiddle the dials and go from one mode to another mode. It's absolutely beautiful. And what I want you to notice, however, in this paper, in the title of this paper, you see the words PT-symmetry, okay? And that's the first time I've really begun to talk about PT-symmetry in this talk. I want you to note that term. So PT-symmetry in quantum mechanics is what I'm going to be discussing now. And this has to do with extending quantum mechanics into the complex domain. So what I'm going to argue is that if you respect PT-symmetry, the eigenvalues can remain real and unitarity can be preserved even if the Hamiltonian is not Hermitian, okay? So I want you to remember a PT reflection is a simultaneous reflection of space and time. And that's what this cartoon over here shows. In fact, if you read this book over here, this is the cover, this is the cartoon on the cover of the book, and that's taken from Alice in Wonderland, as I'm sure you all know. So remember, PT reflection is a simultaneous reflection of space and time, not just space, not just time, but space and time, okay? So here is an example of a PT-symmetric Hamiltonian. This Hamiltonian is not Hermitian, but it's PT-symmetric, okay? Why is it PT-symmetric? Because under parity, x changes sign. So if you look at this term here, x cubed goes into minus x cubed. But under time reversal, as I explained before, I changes sign. So this Hamiltonian, even though it's not Hermitian, it's obviously not Hermitian, it's PT invariant. Now, I first saw this Hamiltonian. I have to tell you this story. I think it's kind of funny. I first saw this Hamiltonian because this is a one-dimensional model of something very fancy that you study in condensed matter theory. It's a one-dimensional model of the Liang edge singularity. And in particle physics, it's a one-dimensional model of region field theory. Okay, same one-dimensional model. Okay. And I was visiting Saclay many years ago, and this was back in the 1990s, and some people there were, some mathematical physicists were looking at this Hamiltonian, and they said to me, because it's a one-dimensional model of these fancy problems in theoretical physics, which I won't talk about today, and they said to me, what do I think about this Hamiltonian? And I said, are you kidding? This is the stupidest Hamiltonian I ever saw because it's not Hermitian. So in short, what I said to them is, the way I see it, this theory is crazy. Okay. Well, many years later, around 1998, I was sitting in a colloquium. And I have to tell you, this was the worst colloquium I ever attended in my whole life. It was a truly terrible colloquium, not unlike this present colloquium, but maybe even worse. And the colloquium was so bad that gradually people in my this is in my physics department, started to get up and leave one by one. And every time somebody got up to leave, the colloquium speaker, who was terrible, would curse them out. It was an amazing performance. I hope I never see another one like that. Okay, and I wanted to get up and get out, but it turned out I was the organizer of that colloquium, and I had invited the colloquium speaker. Okay, by the way, under the suggestion of someone else in my department. Okay, just I want to make that perfectly straight. So I needed to escape, but I couldn't. So I got out a piece of paper and I escaped intellectually, and I tried to think of a problem to work on. And this problem popped into my head, this Hamiltonian. And I thought, let me see what would happen if I solve this problem, if I try to solve this using some perturbative techniques that I had developed in previous years. And to my utter amazement, I discovered that perturbatively, order by order in perturbation theory, the eigenvalues of that Hamiltonian were real, even though the Hamiltonian is not Hermitian. And the way I did it was to say, let me introduce a small perturbation parameter. So instead of treating this Hamiltonian, I replaced 3, the number 3 here, by the number 2 plus epsilon. Okay, so in other words, I said, let's consider this Hamiltonian. Okay, and you notice that if epsilon is equal to 1, you get that Hamiltonian p squared plus ix cubed. Okay, but if you treat epsilon as small, you can do perturbation theory in this small parameter epsilon. And to my amazement, to my absolute astonishment, the eigenvalues turned out to be real. At the end of the colloquium, I ran out, grabbed my graduate student at the time, whose name was Betcher, Stefan Betcher. We got onto the computer, we calculated the eigenvalues for all epsilon. And I want you to notice that here are the energy levels. All of the energy levels are real for all values of epsilon, not just this, this special Hamiltonian, but for all of these Hamiltonians, for all real epsilon from 0 up to infinity, all the energy levels are real, okay? And here are some interesting special cases, the cubic case that I mentioned before, but the quartic case, which is very interesting because it has an upside down potential. And yet I'm telling you that here for epsilon equals 2, the eigenvalues of this upside down potential are real and positive. That's an extraordinarily amazing claim. Okay, here's the case epsilon equals 4, the sextic potential. And if you want to read a proof of spectral reality, the first proof, full, complete proof came out in 2001. This is a review article, which you could read, a very readable article. It's kind of long. The proof is not simple at all. It's a very complicated proof, and it uses some very fancy techniques from complex variable theory. But it's rigorously true that these eigenvalues are real, okay? And I want you to notice that what I'm doing in this equation here is beginning with the harmonic oscillator, p squared plus x squared, and I'm putting in a complex deformation. You notice that when epsilon equals 0, this is just the harmonic oscillator. And you know those eigenvalues are real. The eigenvalues of p squared plus x squared are 1, 3, 5, 7, 9, and so on. Okay. And I'm deforming that Hamiltonian into the complex domain. So I begin with a Hermitian Hamiltonian, but for all other values of epsilon, this is a non-Hermitian Hamiltonian. Okay. So what is PT-symmetry? PT-symmetric Hamiltonians typically are complex deformations of Hermitian Hamiltonians. So the idea here is you begin with a Hermitian Hamiltonian and you introduce a deformation parameter epsilon, okay, so that at epsilon equals 0, the Hamiltonian is Hermitian, and you deform it, you lose the hermiticity, but you keep the PT symmetry. So again, I emphasize, why is this Hamiltonian PT symmetric? Because under x goes to minus x, that's p, and I goes to minus I, that's t, the Hamiltonian is PT symmetric, okay? So here's a very simple example. Here's an additive deformation instead of a multiplicative one. Let's begin with p squared plus x squared as before, the harmonic oscillator. We'll add on a deformation I times x times epsilon. And you can ask, what are the eigenvalues of this Hamiltonian? And it's easy. Here's the Schrodinger equation with the boundary condition. You solve it. It's very easy to do that. And the eigenvalues are all strictly real, positive, and discrete, even though the Hamiltonian is obviously not Hermitian. Okay? And the picture that I've given you is completely generic. So I'll just flash some examples. Let's start with the anharmonic oscillator instead of the harmonic oscillator. We'll begin with p squared plus x squared. We'll deform it. And this is what happens to the eigenvalues. Okay? There's some very fancy stuff happening back here, by the way, but I won't go into that. Here's another Hamiltonian. Let's start with a funny anharmonic oscillator, p to the 4th plus x squared. And again, we'll deform it. And look, all the eigenvalues are real, positive, and discrete. And so in case, if you're getting interested in this stuff and you haven't seen it before, and you want to read a really simple, short, very short article on it, you could read this article in Europhysics News. There's an article on PT symmetry and quantum physics that I wrote back in 2016. You can download this freely on the web. And it's just a few pages, totally non-technical article about PT symmetric Hamiltonians. And if you open the article, you'll see on this page of the article, it's only a couple of pages long, there's a picture here. I took this picture, and this It was the most wonderful thing I've ever seen, actually. I'm a mathematical physicist, and I never really expected I would ever have say anything that could be measured directly in the laboratory. But by golly, this is a PT-symmetric system, and they were able to analyze this system in a laboratory. It had all of the results that we predicted in our studies of PT-symmetric models. This is a PT-symmetric optical laser system. It's a waveguide. This is the laser. This is the source of laser light here. It goes into this long string of focusing lenses and so on, but there's a waveguide in the middle that's very hard to see. And then you detect it. And this is the earliest experiment on optical PT-symmetric systems. Okay. And this is an article, I really enjoyed this. This is an article from Nature, cartoon, not an article, a cartoon in Nature Physics back in 2015. The title of this cartoon was The Top 10 Physics Discoveries of the Last 10 Years. Okay, but this is a cartoon. So if you look carefully, you'll see that every one of these top 10 discoveries is a pun. You notice these are Majorana fermions. Okay, those are hairdos over here. Okay, this is the Higgs boson, not the Higgs boson. Okay, but I was very happy to see that they included in the top 10, they included parity-time-symmetry in optics. Well, that's not actually what they included. They called it parity-time-symmetry in optics. Okay. So you can see people doing research on PT symmetry all over the world. You can see examples of PT symmetry. If you are Chinese, you won't see this easily. But if you look over here, well, let me emphasize it. If you look over there, you will see the PT. This is the direction to the toilets. Okay. This is the character that means place. Okay. So let me give you some nice examples of what you can do with PT symmetry. I want to go back and look at that amazing upside down quartic potential that I claimed had real positive eigenvalues. How could this potential, which is an upside down potential and which looks unstable, how could it have positive eigenvalues? How could it have bound states? It seems crazy. So complex variables explains why such a potential actually has quantum bound states. Okay, and without complex variables, it's impossible to explain this. Okay, so to understand this, let me begin by talking something you learn about in first year undergraduate physics. I want to talk about the simple classical harmonic oscillator. And I want you to remember what they teach you in Physics 101. They teach you that harmonic motion consists of a particle moving back and forth on the real axis. It's a particle on a spring. And they teach you that there's a turning point. So you stretch the spring as far as the energy will allow you to stretch the spring, and the particle stops and it turns around and it goes back again and it goes to the opposite turning point, stretches the spring as far as it can go and it stops and it turns around, it goes back and forth, and it executes simple harmonic motion. Okay, and by the way, I want to emphasize that this is the classically allowed region, and these are the classically forbidden regions. Okay, if you haven't seen that terminology before, maybe this will help. This is an example of classically allowed and classically forbidden regions. Okay, and so the question is, what happens if you are sitting in the classically forbidden region? Well, the naive answer to that question, if you ask your professor, what happens if x is bigger than this turning point? Well, the turning point, remember, is where x equals plus or minus the square root of e. It's where the particle is not moving. So x squared equals e. So this is plus or minus the square root of e. And if x is greater than the square root of e, then x squared is greater than e. But if x squared is greater than e, and the energy has to be conserved, then p squared must be negative. How could p squared be negative? That's crazy, okay? But in the complex world, of course, p squared can be negative, okay? So if you start over here and p squared is negative, it means that the particle is moving in the imaginary direction. Its momentum is imaginary, so it moves off the real axis, and in fact, it goes in a large ellipse, and it comes back to where it started. Okay? So in fact, what is this simple harmonic motion? Well, really what it is not just going back and forth. What this is a degenerate ellipse that is going infinitesimally above the real axis, going around the turning point, coming back infinitesimally below the real axis. That is what this simple motion is. And by the way, these really are ellipses. If you solve Newton's law, you can verify that the particle is really moving in an ellipse. But I want to emphasize these orbits are not Keplerian orbits, because you know that as you go to a large elliptical orbit, say the orbit of Pluto, it takes, Pluto's year is very long. It takes a very long time for Pluto to go around the sun. However, these orbits, by virtue of Cauchy's integral theorem, these orbits all have exactly the same period. So all ellipses, all of these ellipses, including this degenerate ellipse, take exactly the same amount of time. Okay, now, suppose we increase epsilon. So remember, this is the case, epsilon equals 0. But if we multiply by ix to the epsilon and gradually increase epsilon, what happens is that these ellipses begin to droop downward in the complex plane. So when you reach epsilon equals 1, here are those turning points in the complex plane. And again, if you start at a turning point, you have back and forth motion between these two turning points, okay? And if you start somewhere else, you get a bunch of deformed ellipses. These are no longer ellipses, these are deformed ellipses, but they all have exactly the same period. And you see the particle is moving in the complex plane, back and forth in the complex plane, okay? And now you can go to epsilon equals 2, where you end up with this upside down potential. There are now 4 turning points, okay? If you start at a turning point, you go back and forth, okay? And if you start at this turning point, you go back and forth. And if you start away from the turning point, you execute a closed orbit in the complex plane. Here's a closed orbit. But now let me ask you a very hard question that if you only knew real variables, you couldn't answer, okay? If you calculate, it's very easy to calculate how long it takes for a particle on this upside down potential. If you give it a nudge and you let the particle roll off to infinity, how long does it take to reach infinity? Well, it reaches infinity in finite time, and that time is very easy to calculate. So you can ask the question, if it reaches infinity in time t, where is the particle at t plus 1? And it's not at all obvious what the answer to that question is. I mean, the particle still exists, right? But where is it? But we can answer the question by using complex variable theory, because all we have to do is to approach the real axis. And as we approach the real axis, these curves get bigger and bigger and bigger, okay? But they all take exactly the same period, okay? And on the real axis, what happens is the particle rolls all the way off to infinity, and then it whizzes around in 0 time, and it comes back up from minus infinity and comes right back to the origin where it started. Okay, so this is what these trajectories look like. As you go closer and closer to the real axis, the particle whizzes around and comes right back to the origin. Okay, of course, it goes way, way off to infinity, whizzes out to infinity here, and comes right back up again. Okay, now, if you ask, what is the classical probability density of finding this particle? Okay, so I just pick a time, any time at random, and I ask, where is the particle? Where is it most likely to be found? You can draw a probability density, and it looks like this. The particle is very unlikely to be found at infinity because it is going infinitely fast there. And it is very likely to be where it is moving slowest, which is right by the origin. So you notice that the particle is localized at the origin. It's most likely to be found, in fact, at 0. This curve is very much like the curve 1 over the curve that I started my talk with, which is 1 over x to the 4th plus 1. Okay, it's very much like that curve. It's a very simple probability curve, okay? And this is what it looks like. So the particle is actually in a bound state. Classically, it is bound at the origin. It is very unlikely to be found far from the origin, and the probability of it being at infinity is 0. Okay, so what is happening in the complex plane is that the particle, this is the probability density, the particle is very likely to be found near the origin, and then it whizzes around, goes to infinity, and then spends a lot of time here at the origin. So you notice that although we think of that upside down potential as being statically unstable, it is dynamically stable in the complex plane. So when it's moving, it's stable, dynamically stable. And you know, of course, lots of things that are dynamically stable. A top is dynamically stable. A bicycle is dynamically stable. Okay, of course, if it's not moving, a bicycle, if it's static, a bicycle is unstable and it'll fall down. If you want to know why a bicycle falls down, it's because it's too tired. Okay, that's why. Okay, so we can quantize that. And if you do so, you find that the picture is not quite like this, but in the complex quantum case, there isn't just one peak of the probability, but another peak and another one and another one. Okay, you have oscillations like that. And you can quantize the theory just using Bohr-Sommerfeld quantization. You can just integrate around one of those closed loops. You do the integral of p dx, and you set it equal to n plus a half pi. That's just WKB theory. And you will find the eigenvalues very accurately that I showed to you on the graph, okay? So I want to emphasize to you that the instability at x equals 0 is tamed, and complex analysis allows us to tame instabilities. So what you see is that physical systems that seem to be unstable can in fact become stable in the complex domain. Why is this? What's the underlying reason for this? Well, the reason is that if you extend the real numbers to the complex numbers, everything is still true. All of the laws of arithmetic are still true. You know, the commutative law and the associative law, distributive law, and so on. They're all true. But there's one thing that is no longer true, and that is that you lose the concept of ordering. Okay, you can no longer say that a complex number is bigger than or smaller than another complex number. Okay, but when you say that a system is unstable, you are thinking in terms of real variables. You know, the energy is unbounded below. That's what you mean by unstable. So in the complex domain, physical systems that look unstable may in fact be stable. And we discover this over and over and over again. Okay, so that explains why when you have epsilon equals 2, over here, which is a minus x to the 4 potential, the eigenvalues are all real, positive, and discrete. Okay, but I haven't said something to you, I haven't mentioned something that is, of course, very obvious to you. Something has happened when epsilon becomes negative. Okay, you notice that the energy levels are all real and positive when epsilon is positive, but there's a transition at epsilon equals 0, and something funny happens. You notice that this energy level and this energy level, as epsilon goes more and more negative, they become degenerate at this point. And then they seem to disappear. So what has happened, of course, is that those energy levels are no longer real. They've become complex. So we have a region of what I call the region of unbroken PT-symmetry over here, where all the eigenvalues are real, and the region of broken PT-symmetry here, where the eigenvalues are partly real. Okay, notice for this negative value of epsilon, you have this real eigenvalue, this one, and this one, but everything else is complex. These eigenvalues have not disappeared, they've just become complex. And this is called the region of broken PT-symmetry. And this is the PT boundary, which is a phase transition between the region of unbroken PT-symmetry and the region of broken PT-symmetry, okay? And by the way, I want you to notice that at epsilon equals 0, that is the one point where this Hamiltonian becomes Hermitian. So the Hermitian Hamiltonians that you know and love live at the transition between regions of unbroken and regions of broken PT-symmetry, where the energy levels are all real or the energy levels go complex. Okay, so let me summarize. PT-symmetry doesn't conflict with conventional quantum theory, but it is a weaker condition than Hermiticity. If you have a Hermitian Hamiltonian, all the eigenvalues are strictly real. But for PT-symmetric Hamiltonians, only the secular equation is real. So unlike Hermitian Hamiltonians, there are exactly two possibilities. If you have a real secular equation, you know, like a polynomial equation, you can have an all real or a partly real spectrum. In fact, the spectrum could be entirely complex. Okay, so here's an example of broken PT, and here's an example of unbroken PT, with the Hermitian Hamiltonian right in the middle. Okay, so what I want to emphasize is that Hermitian Hamiltonians are really boring because nothing interesting happens. The eigenvalues are always real. By the way, here's our former President Bush giving a speech, but I wonder if you can guess who these yawning people behind him are. PT-symmetric Hamiltonians are astonishing because there is a transition between parametric regions of broken and unbroken PT-symmetry, and this transition is very, very easy to observe experimentally. And you remember I showed you that picture of an experiment that was done only, you know, about 8 years after I began work on PT-symmetry. They observed the PT transition. Okay, that was what they observed and published in Physical Review Letters. Okay, so I want to give you an intuitive explanation of the PT transition. Okay, you notice, by the way, that Putin has a PT in it and Trump has a PT in it, but it's backwards. Okay, so this is a very simple explanation of the PT transition. I want you to imagine a closed box with gain. So what I mean by gain is that this is a closed box and you're putting something in it. You could be putting anything in it. You could be putting energy, you could be putting particles, you could even be filling up with water if you like classical systems, okay? So the quantum mechanical Hamiltonian, you know, there's just a 1-by-1 Hamiltonian for this system. The Hamiltonian is A plus IB, okay? And the reason why it's just a 1-by-1 Hamiltonian, but it has a complex energy, because if B is positive or negative, it could be filling up or decaying exponentially. You know, there could be radioactive decay or radioactive undecay. In this case, it's filling up, okay? So now I want you to imagine that you have two closed boxes, one with gain and one with loss. So this stuff is going into this box and stuff is coming out of this box, okay? So the combined Hamiltonian for this system is A plus IB and A minus IB. These are two non-interacting systems, but one has gain and the other has loss. Okay, an equal amount of loss. Okay, now this system is not in equilibrium, but this system is PT-symmetric because under parity, I interchange the two boxes. And under time reversal, what is going in is now going out, and what is going out is now going in. So this system is PT-symmetric, but the system is not in equilibrium, okay? However, what we can do is now we can couple these boxes. We can just take a pipe and let the stuff that's flowing into this box flow through the pipe and go into this box where it then goes out. And this system can, if the pipe is thick enough, be in equilibrium. That is, the level of stuff in this box and the level of stuff in this box might no longer be changing, okay? So now we have coupled the system, so the Hamiltonian looks like this. This is a PT-symmetric system, okay? Time reversal is just complex conjugation. Parity is just this. And if you commute PT with this Hamiltonian, it goes into itself, okay? Now, if you ask what are the eigenvalues, they satisfy a real secular equation, as I promised. And these are the energy levels. And you notice that if the coupling constant is big enough, the energy levels will be real. And that's when the system goes into equilibrium. There's a transition at G equals B, and that is the PT transition. Okay, the energy is real if G is bigger than B. Okay, so the system is in equilibrium for sufficiently large coupling. So what I want to emphasize in this talk is that PT-symmetric systems lie between closed and open systems. This is a closed system, which is described by a Hermitian Hamiltonian. This is an open system, which is described by a non-Hermitian system. And this is a PT-symmetric system where the energy levels, where the stuff flowing into the system balances the stuff flowing out of the system. This is a very special system. I love this guy's flag, by the way. I like it so much that, I don't know, I'll stand up here. I don't know if you can see me, but I'm wearing my favorite t-shirt. This is my PT shirt, okay? Now I'm just going to take a couple of minutes because I just want to flash a bunch of slides at you. There are both theoretical applications and experimental studies of PT symmetry. In fact, there are many, many papers now on PT symmetry. There are well over 5,000 papers on PT symmetry and PT symmetric systems. Theoretically, their PT symmetric systems are interesting because renormalizing makes a Hamiltonian that was Hermitian into a non-Hermitian Hamiltonian, typically. But it still remains PT symmetric. And you can study the stability of the Higgs vacuum. You can study the asymptotic behavior of the Pan-Lavie transcendence. There are even applications to the Riemann hypothesis. It's really interesting. There are so many applications, okay? And there are lots of experimental studies, waveguides, PT-symmetric lasers, electronic and mechanical systems, atomic diffusion, and so on. There are even studies of fluid instabilities, okay, such as the Rayleigh instability. That's a PT transition, in case you wanted to know. The Rayleigh instability has to do with the formation of clouds, thunder clouds, and that transition from a stable atmosphere to an atmosphere where big thunder clouds are forming, that's a PT transition, okay? So here's just a bunch of pictures of some experimental studies. Here is the first observation of the PT transition using optical waveguides that I showed you before that was published in 2009. Here's an even better study that was published in Nature Physics, a much, much better and more greatly improved study of the previous paper. This is a study of PT-symmetric diffusion done in Shanghai and Rutgers. This is a study of PT-symmetric optics done in Caltech. This is a study of PT-symmetric superconducting wires done in Indiana. This is a study of PT-symmetric microwave cavities, which is also a paper that I showed you before. This is a study of PT-symmetry breaking using cavity lasers. This is a study of PT-symmetric photonic graphene. This is pump-induced PT-symmetric lasers. These are PT-symmetric photonic lattices, not just a single waveguide, but a whole infinite set of waveguides called a photonic lattice. This is a study at Argonne National Laboratory in the US of superconducting wires, PT-symmetric wires. This is a study of fast evolution in a PT-symmetric system using NMR in Beijing. This is a study of PT-symmetric metasurfaces. This is a study of PT-symmetric photonic crystals in Stanford. This is a stunningly beautiful paper. You can ask me about it. I won't talk about it. I won't take the time in my talk, but a study of PT-symmetric wireless power transfer. Unbelievable, which has applications in modern automotive development. It's absolutely remarkable. And this is a beautiful paper, really beautiful paper, where they built an electronic circuit. You remember the explanation I gave you of the two coupled boxes where you're putting water in and taking water out? Well, this is two coupled oscillators, inductively coupled. This is an LRC circuit, another LRC circuit coupled. You put energy into one circuit, you take energy out of the other circuit just using a resistor, okay? And now you have a PT-symmetric electronic circuit, and you can observe the PT phase transition. It's beautiful, okay? This was such a beautiful paper that it was spotlighted for exceptional research. Wonderful paper. In fact, I was inspired by that paper. I wanted to know if I can make an even simpler PT-symmetric system, and you can. This is a mechanical system. These are just two pendula, and they're coupled because they're hanging from the same clothesline, okay? They're driven by electromagnets, and you can watch the PT phase transition, okay? These are the equations. You have one oscillator, another oscillator. Here is the coupling. It's an oscillator with gain and an oscillator with loss, and you can observe the PT transition. And this is a very, very fancy experiment. This is an experiment using whispering gallery microcavities. You can take a tiny, tiny solid state chunk here and here. You can shine a laser on it to get a light beam running around and around in this cavity. Okay, this is just 30 microns wide here. And you can couple them, and you can have one cavity with loss and one cavity with gain just by touching them, and light can travel back and forth between the system with gain and the system with loss. It's absolutely beautiful, and you can watch the PT transition. Okay, so that's a bunch of experiments that I showed you in rapid fire. This is an overview of my talk, okay? And I thought just before I quit, I'd love to say one or two words, if I can take just 2 minutes, really, about some interesting theoretical things you can do. So a couple of theoretical examples. If you've studied quantum field theory, you may have heard of the Lie model. This is an ingenious model. So if you remember the history, you know, quantum field theory came about, quantum electrodynamics, but there was an enormous problem, the problem of renormalization. And, you know, Schwinger and Feynman and Tamanaga got the prize for understanding renormalization and applying it in electrodynamics. But T.D. Lee in 1954 came up with a beautiful model where you could understand renormalization not perturbatively, but exactly. You could just do it in closed form. So his Hamiltonian H consists of two parts, and his theory consisted of three particles called an N and a theta and a V. And in this simple theory, the V particle turns into an N and a theta, and the N and a theta turns back into a V. So you could think of the V as a proton turning into a pi plus and a neutron, or a pi plus and a neutron turning back into a proton, okay, virtually, okay? So the Hamiltonian consists of just counting up the number of V's and the number of N's and the number of thetas, okay? Remember, the energy is just proportional to the mass, so you just count up the number of particles and that's the energy. And then the interaction Hamiltonian says you create a V and destroy an N and a theta, or you create an N and a theta and destroy the V. Now, this Hamiltonian obviously looks Hermitian. However, it's really interesting how fast physics goes. Pauli and Shalane showed in just 1 year later that unfortunately, when you renormalize the theory is no longer Hermitian and ghost states appear. Okay, and that happens because when you do coupling constant renormalization, the unrenormalized coupling constant, that's the parameter that you see in the Hamiltonian here, the unrenormalized coupling constant can be written in terms of the renormalized coupling constant by a very, very simple formula. And remember, it's the renormalized coupling constant that you measure in the laboratory. Okay, so you notice that if the renormalized coupling constant is a little bit too big, then this is negative. So G naught squared is negative. So G naught is imaginary. But unfortunately, if G naught is imaginary, this Hamiltonian is no longer Hermitian, and we get ghosts. So Pauli and Shalane said, this is a sick theory, it's not acceptable. In fact, this is a generic problem in field theory and renormalization in general. It's not just connected with the Lie model, although it was first seen in the Lie model. And you can read about this. If you read Barton's book, he says a non-Hermitian Hamiltonian is unacceptable because it may lead to complex energy eigenvalues, but chiefly because it implies a non-unitary S matrix because of ghosts, and it fails to conserve probability. Okay? So renormalization creates instability. And this is a really hard problem. And lots of people worked on this problem. Pauli himself worked on it. Heisenberg worked on it. Wick, Sudarshan, many people, but no cigar. But 55 years later, we figured out what was going on. In fact, the Hamiltonian, after you renormalize it, is PT-symmetric. And there's absolutely nothing wrong with this Hamiltonian. And there are no ghosts in this Hamiltonian. And everything is perfectly fine. It's a perfectly acceptable theory. Okay, there's absolutely nothing wrong with the Lie model. And in general, there may be nothing wrong with a lot of Hamiltonians that arise when you renormalize. Okay, there's also something, but I won't talk about this now, but there's something in quantum field theory called the double scaling limit. And the double scaling limit produces an upside down potential. But I already told you about the upside down potential in quantum mechanics. This is an upside down potential in quantum field theory. And it turns out, although this looks like a terrible problem, there isn't any problem here. Okay? So once again, PT-symmetric quantum mechanics comes to the rescue. There's also, if you're a mathematician and you like things like this, we have written a bunch of papers on nonlinear eigenvalue problems, which have to do with instabilities of nonlinear equations and bifurcation and things like that. And these instabilities are typical of the Painlevé transcendents, which are very, very famous nonlinear differential equations, which I won't talk to you about at all. But what is remarkable is that you can explain these instabilities of these classical nonlinear differential equations in terms of PT-symmetric Hamiltonians. In fact, Painlevé 1, the first Painlevé transcendent, corresponds to epsilon equals 1 in that PT-symmetric system I showed you. So do you remember that cubic PT-symmetric Hamiltonian that I showed you? He doesn't, but you do. Okay, and Painlevé 2 turns out corresponds with epsilon equals 2. So do you remember he's explaining the PT symmetry to this guy over here? Okay, and do you remember the sextic PT symmetric oscillator, epsilon equals 4? That corresponds to Painlevé 4. Okay, and finally, one last comment. You could study PT-symmetric quantum field theory, and we're now writing papers on PT-symmetric quantum field theory. Here's a recent paper on it if you're interested. And we've been able to conduct some, we haven't completed, this is a very difficult problem. We're not completely done, but we're doing perturbative renormalization of PT-symmetric quantum field theory. Okay, and we are able to calculate the renormalized mass, and the renormalized mass turns out to be real, even though the Hamiltonian is non-Hermitian. Okay. Okay, so thank you very much for listening to my talk. I hope you found it interesting, and I'm very, very happy to answer questions if you have any.